Okay, good. So thank you everyone for returning. And now we're going to hear from my good friend, Ron Peretz. Ron did his PhD at the Hebrew University of Jerusalem in the Center for the Study of Rationality. He was a faculty member at the very prestigious London School of Economics before returning to Israel. He has many broad interests and always has something interesting to say. So Ron, go ahead. The stage is yours.
Thank you for the introduction. So Ziv is not one of my co-authors, but the rest are. So I will just mention the co-authors. So it's Gideon Amir, who sits in one of these cubicles, Itai Arieli, Galit Ashkenazi, and myself. So the title of this talk is Robust Naive Learning in Social Networks. And let me start. Okay, so this is the title. And I will start by removing the word robust. So this is naive learning in social networks is something that we didn't invent. So I will just start explaining what this thing is. And I will start with the network. You can see that I'm excited about my iPad more than the topic. I can't help it, I'm sorry. So I will start talking about the network. So what is a network? A network is just a connected graph. Okay, in this presentation, a network will be a connected graph. So this is a social network. And the nodes or the vertices in the graph, we call them agents, and they have opinions. The opinion of an agent is just a real number. There are some papers that refer to opinions as vectors in a vector space. We will refer to them as real numbers. And usually these numbers will be in the unit interval. Okay, so this is the AI0 is the opinion of agent I at time 0. And we usually assume that there is a certain state of the world, the true state of the world, which we call mu. And at time 0, agent I sees the state of the world plus some noise. And the noise is IID, and we will usually assume that the noise is also bounded. Okay, so this is the initial state. And then the first a very popular dynamics is the Degroote dynamics. So I will explain what it is. Again, this is the network. And we have here agent I. And agent I looks at its neighbors. And every time, the time is discrete. The time in this talk, the time will be discrete. So at any time period, each agent I will update its opinion by replacing its current opinion with the average of the opinions of its neighbors, as you can see in this fancy formula. Okay, so this thing describes a dynamics. The initial opinions are random, but from that point on, everything is deterministic. At any time period, they just update their opinions according to a deterministic rule. Okay. So what can we say, or what people have said about the Degroote dynamics? So this is the first paper by Degroote himself. And this paper refers to finite graphs. And there are two results. One says that the limit of the opinion always exists. Well, what does it mean it exists? You can see here that I have a limit of AI to t. So at other time periods, the limit exists. It need not exist for odd and even. For the limit exists for even periods and for odd periods, but it doesn't have to be the same.
So this is because the neighborhood doesn't include the node itself, because if you have just an edge, it would flip all the time, right?
That's true, that's true. If you took the average of the neighbors and the agent himself, then you would have one limit. And if the graph is not bipartite, then there is actually only one limit. And this limit is a consensus. All the vertices converge to the same value. And this value is given by the stationary distribution of a random walk on the graph. If you perform a random walk on the graph, then it has a stationary distribution, pi, and you just take the average of the initial opinions with respect to that pi. And what you get is the limiting opinions of all the vertices. Okay, this is a classic result by the group from 74. Well, actually, to be precise, the group considered a weighted version of this dynamics, where you take a weighted average of your neighbors. But here we will simplify things, and we always take the simple average of the neighbors. And this is what you get from the group's result. And then a few years later, Golub and Jackson, they found a nice interpretation of the group's result. And they said that if the initial opinions are IID, and the maximum weight of the stationary distribution of the random walk on the graph is small, then the limit is close to mu, to the expectation of the initial opinions. Okay, this is just a simple concentration result. When you take a weighted average and all the weights are small and the variables are IID, then you get, by the law of large numbers, that the probability that the result will be close to the average is high. Okay, so by applying this thing, you get that the limit is close to mu, and this is what they called naive learning. Why is it naive? It's naive because the updating rule is very naive. They don't do any Bayesian updating or some smart things. They just take the average. And why is it learning? Because they end up learning the true state of the world, or at least approximately. They end up knowing more or less what is mu, which is the true state of the world. So they achieve learning and they do it naively. So these are known results. Okay, so let's start with a theorem. This theorem, we proved it in the paper, but I'm not sure it's new. I'm pretty sure many people proved it before us. So it is just a warm-up for this talk. So if you take the group dynamics, but you run it on an infinite graph. Okay, so now you might not have a stationary distribution, or usually you don't have. The random walk does not have a stationary distribution. And we assume that the graph has a bounded degree. It's a connected infinite graph with bounded degree. then the limit need not exist. This is the first observation. You can have some initial opinions, even bounded initial opinions, such that the opinions of the agents does not exist. They do not converge. Okay, this is one observation. And the other thing is that if you do assume that the initial opinions are IID and bounded, I didn't write it, but you have to assume that the initial opinions are IID and bounded, then the limit does exist, and it's mu, almost surely. The opinions converge to the true state of the world almost surely. Okay, so I will not prove this theorem here, but you can try to think about it. It's not too hard, but...
I might have missed something. Can you repeat what is 1 and 2?
Okay, one says that for some initial opinions, the limit may not exist. And 2 says that if the if the initial opinions are IID.
What is the second sub-index here? After the I?
It is 0. AI 0.
In one, in the
second.
No, but in the first one.
The first one, it's 2T. As I said before, in Gollum's, or not Gollum, the Groot's result was that the limit of AI 2T always exists for finite graphs. So for infinite graphs, it need not exist. But if the initial opinions are IID, then it does exist, and it's always mu.
Okay.
Or almost surely. So that's I'm pretty sure people did it before us, but I'm not aware of such a reference. So we included it as theorem 1 in our paper. And we will actually use it for the other theorems. Okay, next. Now we want to assume a situation where some agents do not comply with the Groot rule, with the updating rule. They do something different, and it may change the outcome. And we will consider 2 types of such agent. One is called a bot, and we saw in the literature people sometimes call them stubborn agents or lobbyists. And what is a bot? A bot is an agent who does not change its opinion. It starts with a certain opinion and never changes it. Okay, so let's assume that there is a bot in one of the agents is a bot. So if we have a finite graph, the opinion of the bot will take over. And another type of agents who do not comply we call them distorted monitoring. And these are agents who observe the opinions of their neighbors slightly differently than what they actually are. So we have, for distorted monitoring, we say there is a certain parameter beta, and we say that an agent has beta distorted monitoring if whenever it looks at the opinions of its neighbors, it sees something which is at most beta away from the truth. So it's a bit distorted, and it might change the outcome very dramatically, even if beta is very small. If let's say that you have an agent who always sees the true opinion of the neighbor, plus beta. So he always overestimates their opinions, and if this thing happens in any time period, then eventually the opinion of the entire graph will go to infinity. So such things can really ruin the learning in this environment. And this is what we call fragility of the group dynamics. And this is what's written here. A single bot or an agent with slightly distorted monitoring dictates the consensus. So if you have, in a finite graph, if you have a single bot or a single agent with a very small distorted monitoring, this thing can lead the consensus to wherever you want, regardless of the initial opinions. So this is not good. Here you see, it's not good. So we want to fix it, right? Let's see how we fix it. Okay, so we have a different dynamics. We call it the epsilon degrowth dynamics, or approximate degrowth dynamics. And let me explain what this dynamics is. So this is the degrowth dynamics. You take the average of your neighbors. And in the epsilon degrowth dynamics, what you do is something very tricky. The opinion at time t+1 is the projection of the opinion at time t-1 on the interval around the average of the opinions of the neighbors with the radius epsilon. Okay, so let me draw it. Okay, this is the real line. And this is the average of the opinions of my neighbors. And now this is the interval of radius epsilon around the average of the opinions of my neighbors. And let's say that this is my previous opinion at time t-1. So at time t+1, I will move to here, to this point, because I project my previous opinion on the interval. I take the closest point in the interval to my previous opinion. And if my previous opinion, okay, so this is just my new opinion. If my previous opinion happened to be in the interval, then I do not change my opinion. Okay?
Ron, why are you looking at the previous opinion at time t-1 and not t?
That's a very good question. Thank you. Because this is what works for me. I wish I could prove something with your suggestion, but I don't know how to do it. Okay, so yeah, indeed it looks more natural to consider my current opinion and not my previous opinion, but I don't know how to prove that such a thing works.
Did you try switching between neighbors and oneself, namely take my belief at time t and project it at the average of the neighbors at time t-1?
I have no idea. I didn't try it. No, I didn't try it.
Which has a more compelling story, probably.
But I don't understand what is the opinion at time t, because it is not constructed yet. So what does it mean?
No, he constructs the opinion at time t+1.
Wait a minute. I don't know how to go back. Sorry, I cannot go back. See, I don't know. Probably I should be able to go back somehow. I have no idea. Let's not go back for now. I don't know how to go back. Okay, so I hope you remember what was the dynamics. because now I'm going to state my second theorem, and this theorem says that this dynamics, the epsilon degroof dynamics, converges. So it says that the epsilon degroof dynamics converges, namely AI2T converges on any graph of sub-exponential growth rate and bounded degree, I didn't write it, for any vector of initial opinions. Okay, so we assume that the initial opinions are, I didn't write it here, but we also assume that the degree of the graph is bounded and the initial opinions are bounded. So we have a vector of initial opinions, and these numbers are inside the 0-1 interval, say. And furthermore, the same holds in the presence of bots and distorted monitoring smaller than epsilon. So if the monitoring distortion is smaller than epsilon, and there are as many bots as you want, this dynamics converges.
Sorry, Ron, what do you mean by on any graph of sub-exponential growth rate? So is the graph fixed, or you build the graph as time goes by?
No, the graph is fixed, but if you take
it's an infinite graph, yes?
Okay, I will explain.
You're speaking here of an
graph.
You're speaking of an infinite graph, yes?
Yeah, an infinite graph. It is true for finite graphs as well, but it's more interesting with infinite graphs. When you have an infinite graph, you can take a vertex and count the number of vertices within a given distance to that vertex. And this number grows as the distance grows. And as a function of the distance, this function is sub-exponential. This is what we require. Okay? Actually, we could require that this function is exponential, but with a small enough coefficient, it would be sufficient, as Ron now nods in his head because he sees why.
Okay, thanks.
But so yeah, this is
Ron, can I ask a question?
Yes.
There is something I don't understand with the theorem, because suppose that your graph is a line, okay, so a z, simply z, so the growth is sub-exponential.
That's true.
Now suppose that you have vertex 0 that has initial opinion 0. Then around it you have 100 vertices of opinion 1. So when you run your dynamic procedure, it will the belief will converge to 1. Then around them you have 1 billion vertices with opinion 0. So they will push back the opinion to 0. Around them 1 trillion vertices of opinion, and so on, so that you will not have convergence. So what is wrong in this equation?
This is a very good example that shows that the group dynamics need not converge. But the epsilon, the group dynamics does converge.
And do you have in one sentence intuition why?
I have one sentence intuition. It says it's just because when the opinion, my opinion and the opinions of my neighbors are close enough, then we no longer change our opinions. Okay, in other words, if you look at the fixed points of the dynamics, they do not have to be constant. Okay, I can have a small difference between my opinion and my neighbors, and it is still a fixed point. Okay. Now, what is robust approximate learning? This is what we try to achieve. We want to achieve robust learning, something which is immune to bots and distorted monitoring. We cannot achieve learning, but we can achieve approximate learning. So this is our third theorem, our main theorem. The epsilon, the group dynamics achieves approximate learning. That is, AIT is close to the true state of the world for large enough t. Under the following conditions. Now I'm going to list a very long list of conditions, and I apologize for that. I wish I could get away with some of them. So the first condition is that the initial opinions are IID with expectation mu. And they are bounded IID with expectation mu. This is our first assumption. The second assumption, the graph has not sub-exponential growth rate, but stretched sub-exponential growth rate, which means that the growth rate is smaller than the exponent of x to the alpha for any positive alpha. Okay, so it's a more restrictive assumption that sub-exponential growth rate. For example, graphs with polynomial growth rate, such as ZD, these graphs are stretched sub-exponential. They have stretched sub-exponential growth rate. So it's not an empty set of graphs. We assume that the graph has bounded degree. And there may be bots and distorted monitoring as in theorem 2, namely that the distortion is not greater than epsilon. And the agent for which approximate learning does happen must be far enough from any bot. So there is a certain radius of influence for the bots. So each bot has a certain radius of influence. The neighbors of the bot or agents very close to the bot, they will be influenced by the bot. But those far away from the bot will not be influenced. Okay, so this is in contrast to the Groot dynamics, where when you have a finite graph, one bot influences the entire network, regardless of how big the network is. But with the epsilon, the Groot dynamics, the bot will only have a certain radius of influence. So if the graph is large enough, then most of the agents will not be influenced. Yes, Abraham.
I see your second and third condition. And the question is, in view of the second one, can the bounded degree also be replaced by some bound that says what is the degree as a distance from some initial point?
Maybe, I don't know.
For instance, if it is sub-exponential growth rate, the degree.
I don't know. I didn't try to figure it out. Maybe it's not that important. I don't know. For now, we have this assumption in the paper.
Can you repeat what is the last condition, please?
Yeah, the last condition says that the agent for which approximate learning does happen must be far away from any bot, meaning that the bots have a certain radius of influence. Okay, that's more or less that. If you want to see the precise formulation of the theorem, you have to go to the paper.
Ron, basically, the last condition is like you could have started it before, right? Before you give the condition to say for every I like that, you have this convergence.
Yes, that's true. I wanted to say the complicated things in the end. But yeah, that's true. Okay. And now, furthermore, we don't only work with the epsilon de Groot dynamics, which was our initial motivation, but we created a general framework that allows us to have other dynamics that will satisfy the same conditions. And what the dynamics have to satisfy is 3 properties. We're going to have 3 properties. The first property is monotonicity. Monotonicity means that when an agent updates its opinion, the updating rule is a monotonic function of the history. And when I say of the history, so each agent sees his own opinion and the opinions of its neighbors. That's the history of that agent. And as a function of that history, the function must be monotonic. Actually, I don't think this property is very crucial for the results themselves, but for the proof, it's very important. It helps us in the proof a lot. So we want monotonic rules. Another thing we want it to be approximate averaging. What does it mean? It means when you compare it to what the de Groot rule would do, it has to be close. Our dynamics is epsilon averaging, right? Because we project on the interval of radius epsilon around the de Groot value. So it is approximating the de Groot dynamics in this sense. And the third one is robustness. I will explain what it is later on because this is a bit more complicated. And now what we get from these properties. So if you only assume robustness, which is, I didn't tell you what it is, but I will tell you shortly, then you get the convergence. And robustness, for example, we have dynamics such as the majority dynamics, which also satisfies robustness. Therefore, you get similar results with the majority dynamics for those familiar with the majority dynamics. So for theorem 2, which is the convergence result, you only need property number 3, robustness. And if you combine the 3 properties together, you get the approximate learning result, theorem number 3. Now, let us focus on robustness because it's a bit more complicated than the other properties. Okay, so we define what is gamma and eta robustness. This definition might look a little bit strange. So this is the de Groot value. This is the average of my neighbors. And my dynamics is gamma eta robust if for every value v in the interval of radius gamma around the average of my neighbors, I have the following thing. The difference between my previous opinion and my future opinion times eta, some numbers, a positive number, is bounded above by the difference of the square distance of these values from V. Okay? So this is this magic formula, which I don't want you to focus it right now, but this is the formula, and the majority dynamics, I'm referring to those who are familiar with it, satisfies this condition. So you automatically get convergence. But there are other dynamics that also satisfy this property.
What do you mean by majority when the numbers are between 0 and 1?
So the majority dynamics is just the dynamics that says that at every time, the opinions are either 0 or 1. And at every time period, you take the majority of your neighbors. What the majority says. Okay, you follow the majority. This is called the majority dynamics. And if all the degrees in the graph are odds, it is well defined. If there are some of them are even, then you need a tie-breaking rule for these dynamics to be well defined. But I will not get into it, okay? I just mention it briefly. Okay, but what I do want to show you is another dynamics that satisfies the three properties. This is the granular deGroote dynamics, this fancy name. So what it is you just take the deGroote dynamics, and instead of play or holding the opinion, any possible opinion, you have a finite set of possible opinions. So when you take the average of the opinions of your neighbors, you round them to the closest point in that set of possible opinions. And again, you need a tie-breaking rule. If there's a tie, yeah, there is a rule, but I don't want to specify it here. It's a bit complicated. If you wanted to satisfy the three properties, you need a complicated tie-breaking rule. You can have a set of possible values such that you will very rarely need to use the tie-breaking rules. But anyhow, there is a tie-breaking rule. And this dynamic satisfies the three properties. So you get the result with this. You may say that this is more natural than the epsilon deGroote, or maybe not. I don't know. It is also a kind of approximation of the deGroote dynamics. And it has this property that it is robust. It is not influenced by bots and distorted monitoring.
Can the discretization depend on the player, or should it be the same for everybody?
Yes, you can have a different discretization for different players, I think. Maybe you can even have different discretization in different time periods, but there has to be something in common. So each discretization has different parameters for this gamma and eta. So you have to, you want to have one gamma and one eta, which is good for all of them. So there is some restriction, but you can have different discretizations. Okay. Okay, so now I said these are the results, okay? Now, from now on, I'm going to say a few words about the proof. I don't think I will get to the end of it. So if you want to interrupt me, feel free. And I will just start and go, and we will see how far we get. Okay, so I will prove theorem 3, and inside theorem 3, it includes theorem 2 and 1 as well. So I'm going to use theorem 1 and 2. And in theorem 1, we don't only, theorem 1 is the convergence of the deGroote dynamics on infinite graphs. We don't only prove the convergence, we also say something about the rate of convergence. Okay, and this will be important. And in theorem 2, we're going to use, so theorem 2 is the convergence result for the epsilon deGroote dynamics. And it's going to use a Lyapunov function. For every agent, we're going to have a non-negative function, Li of t, which is decreasing in t. It is non-negative and decreasing, so it must converge. And we show that the variation of the opinion of agent I, actually I should have written 2t, is bounded from above by a constant time the Lyapunov function at time t. So in particular, the variation is bounded, so it converges. But we don't only use the fact that it converges, we use the fact that we can say something about the variation. Okay, so let's see. Okay, so this is the proof now. So we carefully choose a number t, a time period t. I will explain what I mean by carefully later on. And in the first stage, we consider the dynamics up to time t. And in the second stage, we will consider the dynamics from time t onward. But now let's look at the first stage. So we couple our dynamics AIT. This is the epsilon de Groot dynamics. We couple it with the standard de Groot dynamics. And we use monotonicity and approximate averaging to say that the two are not far away. So what we assume, let me draw it here. Okay, so this on this axis we have time, from time t to time 0. And what I marked here is the true state of the world mu. And if you consider the Groot dynamics, in theorem 1, we prove that it is getting close to mu, to the true state of the world. And we even have bounds on the rate of convergence. Okay? And if we take our epsilon de Groot dynamics and we start at the same initial opinion, then we know that it doesn't get too far from the Groot dynamics, because it's an epsilon approximation of the Groot dynamics. So that's the idea. So let's see what we want of this number 2. So we want t to be large enough so that the Groot dynamics gets close to mu with high probability, but we don't want it to be too large because we want the epsilon de Groot dynamics to be close to the de Groot dynamics. So this is what we managed to achieve by carefully finding.
Sorry, Ron,
yes.
Can I interrupt for a minute? Are you looking now at the graph with bots or without bots?
So for now, there are no bots. No bots and no distorted monitoring.
And
okay?
what you are proving is that the epsilon, the Groot dynamic converge? This is the part that you're proving?
That it achieves approximate learning.
Yes.
For now, without bots and without distorted monitoring. I will introduce the bots later on. Now, in stage 2,
on a follow-up question, and graphs are finite or infinite?
They could be either finite or infinite.
So you're...
no.
But you mentioned that the Groot convergence, whereas you told us that it doesn't necessarily converge in infinite graphs. So I'm confused here.
When the IID, it converges, no?
Yeah, when it's IID,
it's IID, sorry.
It converges, and when it's a finite graph, it need not converge to mu, but if the graph is large enough and it has bounded degree, it converges to something close to mu with high probability. Now, after time t, we define two different, we have AIT, this is our epsilon de Groot dynamics, and then we modify it a little bit, then to get A prime IT and A double prime IT. So we modify it a bit upwards and downwards. And we want to satisfy two conditions. First condition is that I prime and I double prime are not far from one another. So they give a good approximation of AIT. And the other property, the important property, is that the Lyapunov functions of the A prime and A double prime are very small. So we managed to do it such that maybe in AIT, the Lyapunov function is large. But when we modify it a little bit, we get a small Lyapunov function. Okay? And now if we use the monotonicity now after time t, we continue with the epsilon deGroot updating rule with all three, with A prime, A, and A double prime. And by the monotonicity property, we have that this order, this inequality is sustained. And if we use theorem 2, the theorem that says that the convergence depends on the Lyapunov function, then we get that A prime at infinity in the limit is close to A prime at time t, and similarly with A double prime. So AIT should also be close, right? So
did you tell us what is the Lyapunov function?
No, I did not.
Okay.
But I can tell you, yeah, I mean, it's a good idea. So let's say that you have a finite graph. How would you prove the convergence of the deGroot dynamics? You take the sum of the differences of the opinions squared on each edge.
Mm-hmm.
And this thing goes downwards, because when you take the average of several values, the thing that minimizes the sum of the squares is the average.
Mm-hmm.
But you have to be careful because you do it simultaneously with all the edges. So what you have to do, you have to go to Ron Holtzman's paper and see how to do it correctly. So you have to take not the values in the same time period, but you have to consider the values of neighbors, but in two consecutive time periods.
Is that the reason why you have the two time period adjustment?
I have it in several places, and yes, that's more or less the reason. But now you have an infinite graph. So what you do, you cannot sum all the squares. You take a weighted sum of the squares. And this is where you need the sub-exponential growth rate, because you want that sum of squares to look like very similar to an average near any vertex, but you want the entire sum to be finite. Okay, that's the idea.
No, if you have considered instead of the difference squared, which gives you the mean, and you take something else, for example, the L1 distance, which gives you the median.
Yeah, that's a very good point. I thought about it, and it really works. There is a dynamics called the median dynamics. So such an argument can work with the median dynamics, which is an interesting thing. And I think, yes, I think it's a good way to go. But we didn't.
But is the median dynamic also non-robust to boots? I would say it will be robust.
I have no idea. I didn't try to work on it too far, but I just know that it exists, and Gidi can tell you more about it because he has a few papers about it. But you get something out of it. That's what I can say. So let's see, now I want to introduce the bots and the distorted monitoring. So with bots, I don't have a big issue, because in the first stage, if I take, if my vertex I is of distance t from any bot, then in the first stage, I will not be influenced by any bot. Okay, so the first stage works. And the second stage, where I take the Lyapunov function, this thing works with bots as well. The same argument with the Lyapunov function works with bots.
Is it not until time t over 2? Do I miss something that you are not influenced?
No, now I think it's just t.
Because somebody that is halfway, in half the time, he might be influenced by the bot, and then you are influenced by him.
We can take it offline afterwards. I'm pretty sure it's T, but
okay.
we can take it offline. Okay, now distorted monitoring. So bots, I don't have problem with bots as long as I'm far away from the bots. Now with distorted monitoring, so if I just take the epsilon, the group dynamics with some beta distorted monitoring, where beta is smaller than epsilon, then it satisfies the 2 out of the 3 properties. So I want to satisfy 3 properties to get things work, but it satisfies only 2 of them. And you can guess which property it does not satisfy. Well, it does not satisfy monotonicity. Okay, it does not satisfy monotonicity. So how you work with it? So you define, so let's say that AIT is my beta distorted dynamics. So I define A plus and A minus to be, they use the same rule as my AIT, but they assume the 2 extreme cases of beta distorted monitoring. Namely, one of them always assumes that the agent observes something which is beta higher than the true opinions of the neighbors, and one always assumes beta lower than the true opinion. So now these A plus and A minus, they do satisfy the 3 properties. Okay, they do satisfy it, and by monotonicity, the A minus is always smaller than my true process, AIT, and A plus is larger than the true process. And if I apply theorem 3 without distorted monitoring to A minus or to A plus, I get the result of theorem 3, which means that they are close to mu with high probability, and this proves my point. This concludes the proof. And now I really hope the animation will work with the last slide. Okay, let's just thank you. All right, that's it. Right on time. All right, I see everyone smiling, so I did my job.
Any questions, anybody?
I have a small question.
Yeah.
If we take it's not a mathematical question. It's about the interpretation of the work, because opinions, you don't control how people form their opinions. Okay. So if it is by the group dynamic, then it's by the group dynamics. So the question is, what you are doing can you test it to say people are not using the groups but using the epsilon the groups, or do you want to change how people change their opinions to have a more robust model? So what's the idea?
So I don't have a good answer, but I have an answer. So I think that there are some papers who try to motivate the group dynamics. But I'm not really, I didn't look closely enough on these papers, but maybe if I do, maybe I will manage to say something similar about the epsilon group. I think maybe it's more intuitive to consider the granular group. Let's say that they have an opinion, but they have a certain precision of, they say a number between 1 and 100. But not fractions.
But given that we observe polarization and not consensus in general in the real world, so what is the perhaps it's the opposite, what we can.
But if we only observe, if the opinions are only 0 and 1,
yeah,
something like that, then you get the majority dynamics. This is a special case of granular degrowth. It is the majority dynamics. And then you should go to Ron Holtzman. He's an expert in majority dynamics. But our result says something about it. It says that it converges, which is a well-known result. But no, that's what I can say about it.
Ron, a question in between your work and Rida's question. So not how people really behave or adjust their opinion, but if instead of taking the average, you would have a structure of a graph by which there is some strength to the links. So each edge connecting one to the other will have some weight, and you will take a kind of a weighted average of the opinions according to these weights. Would anything change?
I think you could get a similar result, but you need some assumptions. You will have to assume that the weights are not too big and not too small, something like that.
Yes, the weights are more than some epsilon. You have bounded degree in these cases. So
yes,
so you all are uniformly bounded away from 0 and bounded.
Yeah, so I guess you can modify the analysis to work with such a thing.
Okay.
Oh, I have a question to myself. So one thing that we wanted to achieve, but we haven't so far, is working with asynchronous time. Meaning that not everyone updates at the same time. The agents have Poisson clocks, and these Poisson clocks ring, but we didn't manage to do it so far. We have some partial results. It's a very interesting. We didn't think it would be interesting, but even simple things become a bit more complicated. We still hope that we can work with this model, but there are interesting things with the asynchronous model.
But just to my knowledge, there are many asynchronous model of voters model, but are there degrowth asynchronous model in the literature?
You can define it. You've just
you can define it, but has it been ever studied? Just the simple model without?
I know that, for example, if you have a finite graph, the opinions will converge to consensus, but the consensus is a random variable. And I hope that maybe I can say something about something like when the graph is large, then the variance of the consensus is small or something like that. But we're in the progress of proving such a theorem.
One more question. Here, the dynamics was a discrete dynamics. What would happen if you would have a continuous time dynamics in which this averaging is only the direction of the change of the opinion of each individual? So you have gradual changes of opinion because usually people don't change immediately. You know, they have some positions, some belief, and they usually make gradual changes to it. So this will define the derivative of the dynamics and not the dynamics itself. Would the results stay the same?
A quick thought about it tells me that it's a very interesting model to work on, but I don't have. But yeah, it's very natural and interesting.
I think in this case you also wouldn't need this epsilon. Yes, maybe you will get this these results even without this epsilon robustness.
I don't. What do you mean by that?
You took here the projection, yes?
Yes.
But here you would never jump far away. So you will always be approaching to this direction of this epsilon, yes?
Yeah,
So
but if you have one bot, if you have one bot, wouldn't it influence?
Yeah, you will have influence. If you don't cut something, you will have propagation of a bot.
Mm-hmm. Okay, so this should probably be adjusted into the dynamics, how to do it, yes. Okay. Even for the model without the bots, I think the continuous version is somehow more natural than the discrete updating.
Yeah, I agree. It's very natural.
But you could have a dynamic. If you had a continuous time dynamic, you could maybe take into account the derivative to take into account the bot to eliminate neighbors which are not changing fast enough.
Yes, maybe.
Because essentially that's what you decide, is that you are filtering people which are not evolving fast enough.
You want to say that when you're close to the opinion, to the average of the opinions of your neighbors, you slow down. Yeah, something like that could work.
Okay, thank you very much, Ron. Very interesting.
Thank you.